So if you can have quiet, please. This is just going to be a brief introduction to Chapter 5 to finish this lecture with, where we're going to look at sequences in R to the D. We're going to revisit the notion of convergent sequence, and I'm going to tell you about another one of my invented terms, which is supposed to help you with convergence of sequences, because I sometimes feel that people have a good intuitive understanding of what it means for a sequence to converge, but yet again, because they're not really on top of the definitions and haven't been used to working with the definitions, sometimes people find it hard to prove things about convergent sequences. And so I've introduced some invented terminology about absorption of sequences by sets, which I think provides some tools that help you to prove things with sequences if you want to do them carefully. However, I'm not going to dwell on it too much because it's a non-standard term again. Other lecturers won't use it. It's going to be something useful for us, but I won't spend too much time on it now. I will come back to it and talk about it a bit more in Chapter 9 when we do something rather sophisticated about sequences of functions. There, I think that this term absorption will be very helpful to us, but you can get along without it most of the time in this module, apart from in Chapter 9. I still think it's worth looking at, and there's lots of question sheet questions on it, which give you a chance to really practice doing proofs, and the notion of absorption gives you a very useful tool that will help you practicing doing proofs. So, sequences. You know about sequences in the real numbers, and now we want to look at sequences in R to the D. And here's a notation we're using. So if I say xn is a sequence subset or equal A, what I mean is this is one of the notations people sometimes use to mean that xn is a sequence. And notice my sequences will start from a first term, term 1, unless otherwise specified. So note, start from n equals 1 unless otherwise specified. And of course, it's an infinite sequence. It doesn't stop. Unless otherwise specified. So if I write that notation, I mean that there's one term for every natural number, and all of the points are in the same set A, because I said contained in A, so I mean all of the xn are in A. And sometimes we'll just write sorry. Sometimes we'll just write xn as a sequence in R to the D this way. And you might have some repeated terms or not. Here's one which keeps jumping backwards and forwards between 2 points of R to the D. So you could write this out in full. So full, this is a sequence. First term is 1 minus 1. The next term is 1, 1. Then 1 minus 1. Oops. And so on. A few more terms of that sequence would have been useful, but I ran out of room. Anyway, you can see what it does. So it goes backwards and forwards between 2 points. That's a perfectly good sequence in R squared. So what does it mean for a sequence to converge in R to the D? Here's the official definition. If you're asked for a definition, you've got to give the standard definition for the notes. People have lost an incredible number of marks on this in past years, so watch out. This is something that has often come up in the exam, and people have lost an awful lot of marks by not giving me a correct definition. So watch out for this one. See the comments on past exams for how people have lost loads of marks on things like this by giving what I call unhelpful answers. So, you've got a sequence in R to the D. What does it mean to say it converges to point A in R to the D? Well, you look at the distance from xn to A, and you can write that as a distance from xn to A. That's Euclidean distance. And that gives you, so whereas xn and a are in R to the d, the norm of xn minus a, or the distance from xn to a, is a real number. It's a non-negative real number. And you know about convergence of real numbers, so you can ask, does it converge to 0 or not? In the usual sense, as in G11ACF, in R. So you now convert a question about vectors into a question about real numbers. In fact, that's in R+. And you can ask whether it converges to 0 or not. Now, this is an equivalent epsilon n notation, and this is one of the definitions you saw in G11ACF. And I will return to this because this is actually a definition that's quite useful to work with epsilon n. So it's for every epsilon greater than 0, there should be some point, some big natural number, little n 0, or you can use capital N if you like, so that for all numbers from that point on, for all little n from that point on, the distance from xn to a must be strictly less than epsilon. So that's an epsilon n definition. Notice, in what we're talking about above, we usually use little n to be an integer, and so you can abbreviate some of that and just say, for all little n greater than n naught, that's just standard mathematical, well, you could say it's being sloppy, but actually it's just a mathematical convention that it's understood that you mean integers in that setting. So I suppose you've got a convergent sequence like that, then you have some alternative notation, but this notation is not the definition. And this is where people have lost loads of marks in exams in the past, because often in past exams I've said, give the definition of convergence of a sequence, and people have said a sequence converges if it tends to some point, which tells me nothing. I need a definition you can work with. I need the standard definition from the module. So you have to give a helpful definition. So these are just notation. Limit n tends to infinity xn is a, or limit of xn is a, or xn tends to a as n tends to infinity. That's just notation, but the definition is what we saw above. Okay, we'll stop there for today.